A qubit is a two-level system, so let's draw that out. So one of the levels we'll call the ground state. We'll call that n equals 1. Now let's put a vertical axis here and have that in electron volts. And then from the ground state, we go to the next quantized state, which is our first excited state, and we're going to call that n equals 2. Now, if we put an electron here in the ground state and then apply some electromagnetic energy, so I'll draw a little sine wave here to represent that, to this system, depending on the frequency of this waveform, because it's a photoelectric effect, we can make this electron jump up to the next quantized state. And when we remove it, eventually it'll fall down and emit the same energy or the same frequency. And that frequency is equal to the energy of the excited state minus the energy of the ground state over Planck's constant. The other thing to consider as well, that electrons are tiny little magnets, so they have poles and magnetic moment. So why don't we define that when it's in the ground state, north faces downwards and south faces upwards, and we apply our electromagnetic energy, and when we move it up, we find to the next quantized state the poles have swapped over, so now north is facing upwards and south is facing downwards, and we call this magnetic moment the spin of an electron, even though nothing actually spins. And when north is facing down, we call that the spin down condition. And when north is facing up, we call that the spin up condition. Another thing that we can do, and this is according to Schrodinger's equations, is that we can also say there is states in between, and there's a probability that this electron could be within a state between this energy level and this energy level. So if we fire an appropriate amount of electromagnetic energy at this system of the correct frequency, we can say with a certain amount of probability that our electron will be somewhere in between the excited state and the ground state. And also the magnetic moment would be somewhere between the spin up state and the spin down state. And it's the spins or the magnetic moment that we actually measure in our quantum system. Now we can visualize this on a unitary circle. So if I draw a circle here, like so, and we can say, we can define our measurement basis, and we'll say a spin down is equal to a vector here on the horizontal axis. And we can say, well, that is a quantum zero state. And we know these are orthogonal. Orthogonal means a right angle. So the spin up condition is orthogonal to the spin down condition, and we can say that in Ket notation is our one state. And in vector notation, x-axis is 1 and y-axis is 0 for this vector, and for this one our x-axis is 0 and our y-axis is 1. Now superposition says there's a probability that there's going to be an electron probably halfway in between. So superposition essentially means that the vector is a summation of these two vectors. So we get one vector here right down the middle, and its Cartesian coordinates are 1 over root 2, comma 1 over root 2. Now we have a full quantum computing system, essentially. When we only had the spin up state and the spin down state, and we equated those to a logical 1 and a logical 0, we essentially had a register that represented a logical 1 and a logical 0. Superposition is where quantum computers get their power and their ability to do exponential calculations much faster than a classical computer. So now we've essentially got a system where we have spin up, spin down, and somewhere in between that we call superposition. Another way to visualize this system, by the way, is on the Bloch sphere. So let me draw a circle like so. This is not a circle, it's a sphere. It has an x-axis, it has a y-axis, it has a depth, a z, axes. And at the top here, these are mathematically related, by the way, but this is where we're using more Cartesian coordinates. Here we use angles, and it's more of a polar system. And so we define the basis state here of a spin down as a vertical vector, and a spin up as a vertical, also as a vertical vector, but facing downwards, and we call that the one state, like that. Now for superposition, let me draw an ellipse here to represent the equator. For superposition, we define that on our Bloch sphere as a rotation around the equator. So instead of orthogonal now, these are opposite, and the superposition state is a rotation around the equator. And we have a horizontal angle here between north and south, and then we have an angle that spins around the equator, and those are the two angles that essentially define what these vectors are. Now we understand that we can have a spin down state, a spin up state, a state somewhere in between with a probability, and that's what we call superposition. We can see that represented on the unit circle, and we can also see that represented on the Bloch sphere. We can go on now to define some gates and do some basic quantum calculations, and that's going to be the subject of the next video.